Hi everyone, hope everyone's doing well. So today what we'll do is we will discuss one more section from chapter 5, and I thought it would be a good idea to actually point out what section this is. This is section 5.7. So today we're going to talk about Fischer projections. There's more that we need to do, but this video is going to focus on Fischer projections. Fischer projections. So Fischer projection, similar in the sense like Newman projections. Like Newman projections allowed us to draw molecules, specifically alkanes. Now you can use it for alkenes as well, but it allowed us to draw alkanes in a different way so that we could analyze the conformations. You know, it was easy to rotate about the carbon-carbon bond and kind of evaluate the stability of the different conformations that we got. Now, Fischer projections, when it comes to stereochemistry, this is another way of drawing molecules, okay? Drawing molecules with chiral centers. So for molecules with chiral centers, and it is specifically useful for in case where there are multiple chiral centers. So it is very useful when you have multiple chiral centers in a molecule, okay? And this is mostly used for sugars. So mostly used for sugars. So this is something that you would need to, basically you would have to retain this till you get to like biochem. Because when you get to biochem, you're going to see sugars. There's going to be a lot of discussion on sugars, and all the sugars, in fact, some amino acids sometimes could be drawn using Fischer projections. But you could do it for one chiral center, but it's mostly applied to cases where there are multiple chiral centers. And it is very useful for sugars because, again, sugars, these have multiple chiral centers. That's the key here. So it's very useful when we're actually talking about sugar molecules. Okay. So now in this particular case, and I guess another thing that I want to add is it makes identifying stereoisomeric relationships easy. Okay, so it actually makes identifying stereoisomeric relationships easy. Now, when we are saying stereoisomeric relationship, in chapter 5, we've talked about 2 stereoisomeric relationships so far. These are enantiomers or diastereomers. Okay, so these are the 2 relationships that we're talking about. So Fischer projections, it actually makes it easy to identify these stereoisomeric relationships. So that's one good thing about Fischer projections. So let's dig into this, and then maybe let's look at some structures and see how this is useful in actually seeing all of these molecules and how are molecules drawn. Okay, so we'll do that. Okay, and we'll start off simple again, looking at just one chiral center to explain how is a Fischer projection drawn, and then we'll build it from there. So if we have a molecule, okay, so let's say we have a molecule like this. Yeah, let's say that's like a very simple molecule that we're looking at, okay? It's not drawn in Fischer projections. We've drawn it in wedge and dash, okay? We've drawn it as a wedge and a dash. So that's a very simple molecule that we're looking at. Now, if we, and so what we'll do is we'll just assign configuration to that so that we can see how this relates to the Fischer projection. Okay, so if we start here, what we can see is the highest priority group. Hopefully you guys are pros at this right now, okay? For this molecule over here, the highest priority group is the oxygen, so that's 1. 4 is the hydrogen. Then we have this aldehyde functional group, which is actually a carbon double bonded to an oxygen. So this is 2 and this is 3. So in going from 1 to 2 to 3, now naturally in this particular case, our lowest priority group is away from us, that's on a dash. So in going from 1 to 2 to 3, we move counterclockwise, and that means this chiral center is an S configuration. Okay, so this is of the S configuration. So now when we have to draw a Fischer projection, what are some things that we need to keep in mind? Okay, so in a Fischer projection, each chiral center is represented by the intersection of two lines. Okay, each chiral center is represented by the intersection of 2 lines. What do we mean by that? Essentially, if we have 2 lines like this point here where they intersect, that's our chiral center. Okay, so that's our chiral center. That point over there is a chiral center. And these here are the 4 substituents that are attached to the chiral center. Okay, so this is a 2-dimensional view of a Fischer projection, or one chiral center in Fischer projection. But in 3 dimensions, the way we read this, okay, so this is the same as our horizontal groups. Okay, so the 2 groups that are horizontal, okay, that's the chiral center. The 2 groups that are horizontal, these are on a wedge. So these are basically coming out of the plane of the board. Okay, that's how it's viewed or imagined in 3 dimensions. So the 2 horizontal groups are on a wedge, and the vertical groups here, okay, those are both on a dash. So the vertical groups are both on a dash. So horizontal groups or bonds, maybe we should say bonds, okay, horizontal bonds are a wedge, okay, and vertical bonds are dash. They're supposed to be on a dash. That's how we imagine this in 3 dimensions. So that means when I'm looking at a Fischer projection like this in 2 dimensions, what I must understand is that there is a chiral center here. there are two substituents or groups on these horizontal bonds, and these two bonds are on a wedge, or are a wedge. That means they're coming out of the plane of the board towards me. And the two substituents, or the two bonds that are horizontal, they are a dash and they're going behind the plane of the board. So that is how I view this in, in 3 dimensions. Now, if we kind of relate this to our molecule here, if we look at the chiral center, okay, if you look at the chiral center, our chiral center has 4 different groups. There is a methyl group, there's an aldehyde group, there's a hydroxyl group, and there's a hydrogen. Now, by convention for sugars, we usually put these the aldehyde group, or which is actually the most oxidized carbon in the molecule, that is actually placed at the top. But this does not have to be followed, but this is a convention that you're going to see for sugars. Whenever you look at a sugar molecule, that's a conversion that will be followed. So it's always considered to be at the top. So it's on the top of this vertical bonds. And then the carbon chain, which is basically 1, 2, and 3. So we have 1 carbon, which is the aldehyde here. Second carbon is our chiral center. And then the third carbon is a methyl group. It is considered to be vertical. So we have a methyl group here. That methyl group is over there. Okay, so the carbon chain is usually kept on the vertical bonds, like throughout. And that leaves us the hydroxyl and the hydrogen, which are on a wedge on a dash in that diagram, but that doesn't matter. We can place them here, and then we'll try to evaluate the structure. Okay, so let's say I put the hydroxyl group here, and I put the hydrogen over there. Okay, and I've just arbitrarily done that. And we will now evaluate if we actually got the same molecule or not. How would we know that? What would tell me if I've drawn the same molecule or not? It's the configuration. Because what I know is that this particular chiral molecule, or this particular stereocenter in the chiral molecule, was of an S configuration. And that chiral center is right here. Okay, so what we have to do is we just have to evaluate if we basically retain that S configuration here. And we've already assigned priorities over here, so we can go ahead, put the priorities down. So we have 1, and this is 2, and this is 3. The hydrogen is 4. So now if you look at it, in going from 1 to 2 to 3, we move clockwise. So this is a clockwise rotation, which would mean R. Okay, this is a clockwise rotation. So that's R, but our lowest priority group, the hydrogen, is on a wedge, which means I should invert, should be the other configuration. So the actual configuration is an S. So that means this molecule, this compound that I have drawn in Fischer projection here, is the same as this molecule at the top, because they are both of the S configuration. Now, how do I translate this to a 2-dimensional Fischer projection? So this is Fischer projection in 3 dimensions. Now, how do we translate this to the Fischer projection in 2 dimensions? I basically put the groups wherever I see those. So that's where the aldehyde is, the methyl is here, the hydrogen is on the right, and the hydroxyl is on the left. So I basically transferred all the information from here to the 2-dimensional molecule. And this is how you would see a Fischer projection most of the time. But again, just to emphasize again, just to recapture it, but when I see a Fischer projection like this, what I need to know is at the intersection here, there is a chiral center. That's how I'm going to view it. Okay, there's a chiral center over there. the two groups that are on horizontal bonds, these are on wedge bonds that are coming out towards me. The two groups on vertical bonds are on dash bonds that are going away from me. Okay, so that's how we would read this structure. So essentially like this. So although we would be seeing this all the time, we should be reading it like this. Now, just to emphasize this and to like make a point, you know, or just to like show you how my other Fischer projection would have been wrong. Okay, so if I did the other way around, how that would have been wrong. So let's say I had drawn, or we'll stop here. I think that's good. Instead of confusing you more, I think we'll just stop right here, or maybe I should go ahead and do it. Okay, so let's say, what if, okay, this is an if, okay, if I did this, aldehyde, metal, so I've kept the aldehyde and the metal at the same position, like here, but what I'm going to do is I'm going to swap these two. So I'm going to put the hydroxyl on the right-hand side and the hydrogen on the left-hand side. So let's say if that's a Fischer projection that I start with, now I can transfer all the priorities here. So this is 1, this is 2, it's 3, and that's 4. And now if I assign configuration to this, if I assign step configuration to this, in going from 1 to 2 to 3, this is a counterclockwise rotation. It is an S, but the lowest priority group is on a horizontal bond, which is a wedge. So it's coming out at me. So that means I should flip this, and the actual configuration is R. And so what we've drawn here, this is not this molecule, but it's the enantiomer of that molecule because it's of the R configuration. Okay, so let me clean this up and I'll draw it again so that we can talk about it a little bit more. Okay, so how does it make life easy for us when we go to like more chiral centers? And in fact, we will redraw those two molecules just to show you how this helps, you know, or what's the sort of what sort of relationship are we talking about here. So we have metal, and I think for my first structure I had placed the hydroxyl on the left and the hydrogen on the right. So we had 1, 2, 3, and 4. So 1, 2, 3 clockwise, but hydrogen is on a wedge. So this is S. Now, if I have to draw an enantiomer for this molecule, it's really easy now. Because if I consider a mirror plane over there, the enantiomer for this molecule should be this structure, which is basically its mirror image. And now if you assign configuration 1, 2, 3, 4, so in going from 1 to 2 to 3, counterclockwise, but hydrogen is on a wedge, which means this is R. So what you notice is we are able to draw the enantiomers really easily, okay? And always remember that if one of your enantiomers is of the S configuration, then the other enantiomer, or if a molecule is of the S configuration, its enantiomer must be of the R configuration, of the opposite configuration. Okay, that's how you would see. So this is how Fischer projection makes kind of life easy for us. And now we'll see it on like maybe a molecule with 2 chiral centers, you know, and that would basically help you see why this is easy to like identify enantiomers and diastereomers and things like that. Okay, so we'll look at a molecule where there are 2 chiral centers. So I think I'm going to start off with just the two-dimensional diagram, and we'll try to draw a Fischer projection from there. Okay, so let's say we have a molecule where we have an aldehyde. Okay, and now again, an aldehyde group is something that's very prevalent in sugars. So you would see most sugars have an aldehyde or a ketone, you know. So this is something that's going to be very common as long as we're talking about sugar molecules. So let's say we have a molecule which is like that, CH2OH. Okay, that's molecule. And I'm just going to arbitrarily put, let's say, a hydroxyl on the wedge here and a hydroxyl on the dash on that carbon. Now notice how my molecule has two chiral centers. There is one here and there's another one over there. Now for this molecule here, the hydroxyl is on a wedge. That means there is a hydrogen that's on the dash. The hydroxyl is on a dash. That means the hydrogen here is on a wedge. Okay, so what we'll try to do is we'll try to draw a Fischer projection based on this molecule. But before we do that, we have to be able to, we must identify the configuration of this molecule because we need to know what we are going to draw. Okay, so let's say for the first chiral center here, if I were to assign configuration for this chiral center, again in this scenario, this hydroxyl or the oxygen that's connected to the chiral center is 1, that's the highest priority group. This carbon here is going to be 2. This carbon is 3. Okay, and the hydrogen is 4 and it's on a dash. So in going from 1 to 2 to 3, 1 to 2 to 3, we move counterclockwise and the hydrogen is on a dash. That means this stereocenter is of the S configuration. Okay, let's move to the other stereocenter now. Now for this stereocenter here, again, the highest priority group is the oxygen. That's a 1. Okay, and then we have this carbon and that carbon. So the carbon on the left versus the carbon on the right. The carbon on the right is connected to 2 hydrogens and 1 oxygen, whereas the carbon on the left is connected to 1 oxygen, 1 hydrogen, and 1 carbon. So this gets a higher priority. So this is 2 and that's 3. Hydrogen is 4. And now in moving from 1 to 2 to 3, when we look at the rotation, okay, when we look at the rotation, this is a clockwise rotation. This is a clockwise rotation, but the hydrogen is on a wedge. That means clockwise is R, but the lowest priority group is pointing towards us. So we have to invert, and that means this is also NS. So what we have here is a molecule which has 2 chiral centers. They are both of the S configuration. Now, we're going to convert this molecule into a Fischer projection. So that is all we're going to do on this board here. And then we'll take the Fischer projection and we'll try to draw its enantiomer and diastereomer and everything. Okay. So let's see. We have this molecule here. So there are 2 chiral centers in this molecule. That means my Fischer projection should have 2 kind of crosses to it. Okay, there should be 1 vertical line, 2 horizontal lines, because each of these intersections is basically a chiral center. Okay, we have 2 chiral centers and we have 2 chiral centers here now. Now again, our carbon chain is 1, 2, 3, and 4. That's how a carbon chain goes. So, and as I said, for most sugars, the most oxidized carbon, which is the aldehyde, shows up at the top. So we're going to put the aldehyde over there. Okay, and then we have the second carbon, the third carbon, and then the 4th carbon at the bottom is a CH2OH. So we have the aldehyde carbon, then we have one chiral center, another chiral center, and then a CH2OH. So basically put that. Now, on the first chiral center, we have a hydroxyl group and a hydrogen. And we kind of have priorities over here, so we can use this. So let's see what would happen if we put the hydroxyl group on the left-hand side and the hydrogen on the right-hand side. And based on these priorities, what I know is this is 1, this is 2, the hydrogen is 4, and then the other chiral center, this is 3, as far as the first chiral center is concerned, because that is what I see in my picture over here. Okay, so the other chiral center is 3. So now if I look at it, in going from 1 to 2 to 3, okay, 1 to 2 to 3, this is a clockwise rotation. The hydrogen is on a horizontal bond, which, recollect that a horizontal bond is a wedge. So this is a clockwise rotation, which is R, but the lowest priority group is on a wedge pointing towards us, and that means this chiral center is S. So that means we actually transferred the same stereochemistry. So in this wedge and dash picture, our first chiral center was an S, and we have it as an S here in the Fischer projection as well. Okay, so the hydroxyl on the left, hydrogen on the right gives us the right stereochemistry. Now what we'll do is we'll do the same for the next chiral center. We'll put hydroxyl on the left and hydrogen on the right. And we'll see if this is what we want, or if this is wrong, okay? And again, taking the priorities from this wedge and dash picture, the hydroxyl is 1, the first chiral center is 2, CH2OH is 3, and hydrogen is 4. Okay, so I've basically transferred all the priorities from here. And so in going from 1 to 2 to 3, 1 to 3, this is a clockwise rotation again. And the hydrogen is on a horizontal bond, which is a wedge. That means, so clockwise means R, but the lowest priority group is on a wedge. So this is also an S. So essentially what we got here is this exact molecule. Now, let's pretend as if this is not what I did, okay? Again, let's say I had initially put the hydroxyl on the right-hand side and the hydrogen on the left-hand side. Let's say this is what I did. Then my priorities would have been 1 and 4. Those do not change. The priorities are still the same. And now what you can notice is in going from 1 to 2 to 3, 1, 2, 3, this is a counterclockwise rotation, which is S, and the lowest priority group is on a wedge. So we have to invert, and then the configuration in that case would have been R. Okay, that would have been R. But this is not where we started, because we started with a wedge and dash picture where where both chiral centers were of the S configuration. So what we have here is wrong. And so with Fischer projection, the good thing is if you get to the wrong configuration, all you have to do is swap 2 groups and essentially swap the 2 horizontal groups, and it would basically fix it for you. So putting the hydroxyl on the left-hand side and the hydrogen on the right-hand side would give us the the S configuration. So this is 1 and this is 4. So 1 to 2 to 3 clockwise R, but hydrogen is on a wedge, so it is S. So we got the right configuration. So we basically converted this wedge and dash drawing into a Fischer projection right now. That is what we've done here. And so let me just capture this. So we have the aldehyde, You have the both hydroxyls on the left-hand side, hydrogens on the right-hand side, and the CH2OH. So that is the molecule that we want. So now we will use this molecule and we'll see how Fischer projections make drawing enantiomers or identifying enantiomers, diastereomers, all of that easy. Okay, why is that easy? You know, why are these useful when we get to these molecules with multiple chiral centers? And that's the key. And that's when it is useful, because we might be looking at a really big molecule with a lot of chiral centers, sometimes like 3, 4, 5, and 3, 4 actually for sugars for most of them, but there could be bigger molecules, you know, and so it becomes easy. So I'm going to redraw that molecule. So what we had is we had aldehyde at the top, CH2OH at the bottom. Both hydroxyl groups were on the left-hand side, both hydrogens were on the right-hand side. These are our two chiral centers. I'm just basically recapturing that image that we had. And what we said is this molecule here has S and S. Both chiral centers are of the S configuration. Okay, both of them are of the S configuration. So now that we have the Fischer projection, and let's say if you want to draw its enantiomer, what would be its enantiomer? It would be this molecule here. Now you see how having it in Fischer projection makes it really easy for us to see that if we have this molecule and if there's a mirror here, that is what we're going to see. That's its mirror image. And since that is the mirror image, and this is the enant, and these are non-superimposable, so we cannot superimpose these, okay? We cannot superimpose this, so this one should be R, and both chiral centers there should be of the R configuration. They should both be R configuration. Now you can verify this if you want. So again, translating, and we can do this for like maybe one of the stereocenters. So translating all the priorities, this was 1, this was 2, and this was 3. So this is 1, this is 2, and this is 3. And naturally that is 4. So in this mirror image that we've drawn, in going from 1 to 2 to 3, this is a counterclockwise rotation, and the lowest priority group is on a wedge, which means this is R. And we'll basically find the same for the other stereocenter also, if you were to work through this. Now, let's say if I draw another Fischer projection of this molecule, of the same molecule, okay? And we'll call these structure A, this is structure B. What I'm drawing now is structure C. If I draw another mirror image, another Fischer projection of this molecule. And okay, I'm going to keep the carbon chain the same. So we have CH2OH. And essentially what I'm going to do is I'm going to keep the first stereocenter the same. So OH and H. But the other stereocenter, I'm going to flip the two groups. So we have hydrogen and we have hydroxyl over here. So now, if I compare this structure to the top structure A, if I compare structure C to structure A, our arrangement around the first stereocenter, okay, about this stereocenter here, the top half of the molecule, that is kind of retained. It is pretty much the same, the exact same arrangement. And so this stereocenter is still going to be an S configuration. But our arrangement around the bottom half of the molecule, or the second stereocenter to be specific, okay, so that arrangement now, two groups got swapped. So these two groups got swapped, which means this should be now the opposite configuration because two of the groups got swapped. So if you look, this should now be an R configuration, and I would encourage you to actually verify this. So go ahead, assign priorities and work through it. Convince yourselves that this is indeed an R configuration now. Okay, so, and let's say we draw another one, CH2OH. And now what we're going to do is, relative to the first one, this is D, relative to the first one, we're going to keep the bottom half the same. So the second stereocenter the same. So the hydroxyl is on the left, hydrogen is on the right. And the first stereocenter, we are going to swap the two groups. So we get hydrogen on the left, hydroxyl on the right. So that's our first stereocenter. So we basically swap those two groups. And so now, since this first stereocenter was an S configuration here, it should be R in structure D. The bottom one, the second stereocenter was S configuration. The arrangement is the same, so this is also an S. Okay, so it basically helps it easy to identify all of these relationships. And now, what is interesting is, if you look at it, what you should notice is that we can identify some relationships here. So it turns out A and B, as well as C and D, okay? A and B and C and D, notice how these are mirror images of each other and they're non-superimposable. So these are enantiomers of each other because they're related to each other as non-superimposable mirror images. Now, if you look at A and C, A and D, B and C, as well as B and D. If you look at all of those molecules, between A and C, one of the stereocenters is of the same configuration, the other stereocenter is of the opposite configuration. So one stereocenter is retained, the other one got inverted. What do we call those molecules? They are diastereomers. Similarly for A and D, one stereocenter is the same, is retained, the other stereocenter got inverted. So diastereomers again, between B and C. One stereocenter is retained, the other stereocenter is inverted, diastereomers. Between B and D, one stereocenter is retained, the other stereocenter got inverted, so diastereomers. So basically, all of these are diastereomers of each other. So they are all diastereomers. Okay, so we can identify these relationships much easily compared to like the wedge and the dash drawings. So that's the biggest advantage to Fischer projections. Okay, so what we'll do is we'll try to draw another molecule and then we'll try to see if we can identify how the molecules are related to each other and maybe assign configurations as well. Let's do another example. Okay, we'll do another problem as an example. Okay, so I'm going to go ahead, erase all of this, and I'll draw a few molecules and we'll assign all of these stereoisomeric relationships. Okay, let's say we have a molecule where we have methyl, methyl, there's H and Cl, and we have Br and H. And okay, so let's say those are 4 molecules that we've got. And I've just basically, I mean, I have a plan in my head when I've done this, but I've basically like drawn 4 structures for you. And so the question is, can we, just based on these structures, do you think it's easier to identify the enantiomers here? Okay, let's say if we label these structures with some names, so let's say if this is A, that's B, we have C and D. Okay, is there a structure here which looks like the mirror image, which looks like the mirror image of A? And what we have in A is methyl at the top, methyl at the bottom. Both hydrogens are on the left, Br and Cl on the right. So I think the mirror image would be methyl at the top, methyl at the bottom. The 2 hydrogens which are on the left should be on the right in the mirror image, and the Br and the Cl should be on the left. So look at it, structure D is pretty much that. That means these 2 are enantiomers. Okay, these 2 are enantiomers of each other. Now, we just did that based on whether they are mirror images of each other or not. Let's try to assign configurations and then do the same thing. So work through some of these relationships by assigning configurations. And that's the, and I think that's the most foolproof way to identify if molecules are related to each other as stereos or like enantiomers or diastomers. So let's start with this first chiral center here. So for the first chiral center, on that chiral center, if I look at everything that's connected to that chiral center, the bromine is the highest priority, hydrogen is the lowest priority. That carbon versus this carbon has a chlorine attached to it, that carbon only has 3 hydrogens attached to it. So this is second priority, this is the third highest priority. And now in going from 1 to 2 to 3, when we do this, this is a clockwise rotation, which would mean R, but the lowest priority group is on a wedge pointing towards us. So that means this is an S. That's actually an S. So for the second stereocenter here, highest priority group is 1 there, 4 is here, this is 3 again, and that's 2. Because carbon versus carbon, this carbon has 3 hydrogens connected to it, that carbon has a bromine connected to it. So that gets a higher priority. So I'm going from 1 to 2 to 3. We move counterclockwise, which is S, but the lowest priority group is on a wedge, which means this is R. So the first chiral center is S, where the bromine is attached, that's S. The second chiral center where the chlorine is attached is R. And let's go ahead and do the same for this molecule here. Now we have the priorities here already. So this is 1, this is 2, this is 4, and this is 3. And going from 1 to 2 to 3, this is a counterclockwise rotation. The hydrogen counterclockwise rotation is S, but the lowest priority group is on a wedge, which would make it an R. And so what you notice is now that's the opposite of what we had in structure A. For the second stereocenter, 1, 2, and 3 with 4. So 1, 2, 3, clockwise rotation, which is R. So clockwise rotation is R with the lowest priority group on a wedge. So that's the hydrogen. So this is S now. So we got the exact opposite of what we got inverted stereocenters. So S became R became S. That means these are enantiomers of each other. And that is what we basically say. Now you can use the same relationships, or now that we've worked through one of these, we can basically transfer or assign configurations to the other molecule. So if I look at structure B, compare it to structure A, what I see is that the arrangement around the first stereocenter is retained. So that means this is also S. If I look at structure C, compare it to structure A, the arrangement around the first stereocenter is swapped. So there is two groups got swapped. Hydrogen was on the left, Br on the right. Now the Br is on the left, hydrogen on the right. So that means it must be of the opposite configuration. So that's R. Going to the second stereocenter here, comparing that to structure A. So second stereocenter in structure B compared to structure A is swapped. So chlorine and hydrogen got swapped. So it is of the opposite configuration now. So this was R here. So this is S. And similarly for structure, comparing that to the top structure A, everything is same. And so this bottom stereocenter is R. And so now if we look, we can see other relationships, and we could have seen this otherwise, you know, that structure C is basically a mirror image of structure B. So if you take this structure, imagine this close to structure B, what you see is B and C are mirror images of each other. So they are enantiomers of each other. And that's essentially what we're seeing in the configurations. This is R and R, that's S and S. Okay, so these are also enantiomers. So these are also enantiomers. Now, between structure A and structure B, one stereocenter is retained, the other stereocenter is inverted. So that means these are diastereomers. Okay, between structure A and structure C, one stereocenter is retained, the second stereocenter. The first stereocenter, or the top stereocenter, is inverted. So these are also diastereomers. And then as you work through this, you would realize that C and D are also diastereomers, and B and D are also diastereomers. Okay. Now, again, remember that diastereomers are stereoisomers that are not related to each other as mirror images. So they are not mirror images of each other, but they're stereoisomers. And that is exactly what we see between A and B or any of the other set of diastereomers. So if I compare A to B, it seems like the second stereocenter here, the bottom half of the molecule, looks like the mirror image of the bottom half of the molecule in B, but the top of the molecule is not a mirror image. So they're stereocenters, but they're not mirror images of each other. So they're diastereomers. So that's basically Fischer projections. So what I did is I walked you through what Fischer projections are, how these are visualized, or how these are kind of, visualized in space. You know, so what you have to remember is every crossing point is a chiral center. Horizontal bonds are on wedges coming towards us. Vertical bonds are on dashes going away from us. Okay, and then it basically makes life easy when we are talking about molecules with multiple stereocenters. or for just one stereo center, doesn't matter, okay? So that is a discussion on Fischer projections, and this is section 5.7 in the textbook. We have 2 more sections to cover after this, which I will post in subsequent videos.